So if we continue on then, after that last example we worked, it's a good, really good example to get us started. Let's continue talking about the second law. And we said there's two ways we can, or we're saying here, there's two ways we can increase. And I don't love the idea of two ways we can increase. I think I should add or change. There's two ways we can increase or change the entropy of a system. One of those could actually decrease. I could increase or decrease the entropy of a system through heat transfer. So if I heat up, we talked about my water earlier, so if I heat this water up, the molecules become more chaotic. And so they become more unpredictable, and therefore I'm increasing their entropy. So I can add heat and increase the entropy. I can remove them. I can put it back in my fridge and cool them down, and that will decrease the entropy. So I can increase or decrease. I can change the entropy of a system via heat transfer. I can also increase the entropy of a system through what we call irreversibilities. We talked briefly about these in chapter 6 in a previous lecture about these are things that, like friction, for example, these are things that convert good mechanical energy into non-mechanical forms. That is an irreversible process. Once I've done that, the non-mechanical forms of energy are more chaotic. Basically, I've generated entropy to do so. So what you're looking at mathematically here is we're saying that this is this integral of dq over t. That's what represents mathematically this quantity, the exchange via heat transfer. That's what we're saying here is as I add or remove heat from a system, I'm going to change the entropy of the system through this mechanism. And then the irreversibilities, these are the things that are going to generate entropy. So mathematically, those are the two ways that I can change the entropy of a system. And through entropy generation, I can only increase it. An isentropic process is one where the entropy of a system does not change. Iso, or isen in this case, referring to constant. It's a very common prefix will apply to words that where a property is constant. So isentropic, meaning isoentropic or constant entropy. How does that occur? Well, there's kind of a couple of options, but the most common one that we see is a scenario where if I look at my entropy change and I say, well, that's equal to the integral of d, and I'm using little s's there. So this is integral of d little q over t plus little s gen. So if it's adiabatic or well insulated, that means that just like we saw earlier, we add up a whole bunch of zeros and we still get 0. If it's reversible, that means it's not generating entropy. So if it's adiabatic and reversible, that means it's isentropic. The change in entropy is 0. Now I'm going to put something up. I'm going to pose something to you. It's very important here. There's two things needed for something to be isentropic. Adiabatic is one of those things, right? And I see a lot of students will make the mistake of saying, well, if it's adiabatic, so it's isentropic. No, that's part of it. If it's adiabatic, that's part of what's going to allow it to be isentropic. The other thing is that it needs to be reversible. If it's adiabatic and reversible, so plus reversible, and then I'm going to draw an arrow here. I'm going to draw an arrow here. If it's adiabatic and reversible, that tells us it's isentropic. But I've got to have those two things to assume isentropic. Or at least if I have those two things, that does tell me it's isentropic. Because what I've got here is I'm saying that, again, the integral of dq over t plus the amount of entropy generated is equal to the change in entropy. So if this is 0 and this is 0, then this is 0. This change is 0. Now, the reason I'm drawing an arrow is notice that This could be negative. I'm going to let that sink in for a second. I'm pausing for dramatic effect. Notice that this could be negative. This can be negative. Now, this can only be positive to the best of our knowledge. We don't think we can destroy entropy. We think we can only generate it. This can be equal and opposite of this. These two can add up to be zero. So I can have a constant entropy situation where this plus this is equal to zero. That's the reason for the arrow, right? Because this can be negative and this can be equal and opposite of this, so these can add up to be zero. However, if I know this is zero and I know this is zero, then I know this delta has to be zero, hence the reason for the arrow. If I know this and I know this, then that tells me that. If I know it's isentropic, that doesn't necessarily mean that it's adiabatic and reversible. This could be the negative opposite of that, hence the reason for the arrow. I've said that like 2 or 3 times, and I can give us some examples to think about. I like to point to a cell phone charger. I can have a cell phone charger that once it kind of gets up and is operating at a steady state, kind of an equilibrium where it's losing heat. We know it's losing heat because I can feel it, and I can feel that it's warm. So that means it's losing heat to the environment. So that cell phone charger could be operating at a point where it's losing heat at the same rate that it's generating entropy, right? And if the thing's not getting ready to blow up, if it's just kind of reached an equilibrium, then its internal entropy should hopefully reach a point where it's not increasing any more than it already is. It's basically reached kind of its top level. So that's a perfectly good example is an electronic device that is losing heat at a high temperature and it's maintaining constant entropy. The device itself is not becoming more entropic, but it's generating entropy as it does that. So it's basically losing heat divided by temperature at the same rate that it's generating entropy. And so this sum is zero. That's, again, for an electronic device kind of operating at an equilibrium. That's a good example I can give you, a scenario where isentropic doesn't necessarily mean adiabatic and reversible, but adiabatic and reversible does mean it's mathematically isentropic. If this is 0 plus 0, then this delta has to be 0. All right, hopefully that helps. I've tried to lay that out 2 or 3 different ways. Again, one of the big take homes I want you to understand is just because you can determine from a problem statement that it's reversible doesn't mean it's isentropic. And just because you can determine from a problem statement that it's adiabatic doesn't mean it's isentropic. I need both of these. So that's a common rookie mistake I'll see students make is, well, it's reversible, so that means it's isentropic. No, that's not what that means. It just means S gen is 0 if it's reversible. It doesn't mean delta S is 0. There's 2 things that control that. Okay. Let's go back to the slides. I'm kind of sighing here. I've said that several ways, and I'm hoping it sinks in. And I'm happy to work with students as they encounter it. It's like, well, anyway, I'm sighing out of frustration because I know somebody's still going to struggle with. Well, it's adiabatic. That means it's constant. It's isentropic, right? No, it's not necessarily what that means. All right. That's normally kind of a nice stopping place for lecture 17. I'll go ahead and stop there and we'll start lecture 18 from there. This is probably a short video and that's perfectly okay.